I think we'll go ahead and start, Steve.
All
welcome,
right, okay.
everybody. Yeah, welcome, everybody. I'm Ed Armstrong, and my colleague there, Steve Oldings. We're going to be your moderators this afternoon. I'm going to be doing more of the formal emceeing. So we're here to talk about, for this session, we've organized this little group called NASA ESCO that you've probably heard about, but Steve will kind of like give a little overview of it. We want to, see what's the purpose of motivation was to see what's on the roadmap for the latest kind of best practices, information principles, data formats, and services. And so we've assembled, 4 exciting speakers that we'll hear presentations from. They'll each kind of present in full, and then at the end of that collection of presentations, we'll open it up for some Q&A. But I encourage you also to put in questions in the chat as the speakers are presented. There's also a Slido poll. Maybe somebody can paste that link again in the chat. Of course, it's in the Google Doc. And please, fill in your name and affiliation in the Google Doc. That's actually posted in the chat as well. So we'll do like about 15 minutes. We'll have some flexibility for some more time, of course. But then we'll move into a Q&A session at the end with the remaining time we have. So having said that, I think I'll just go ahead. I think we're ready to go with our first speaker, and that will be Steve Olding, who will give us an overview of ESCO. So go ahead, take the floor, Steve, and go ahead and share any presentation if you have it.
All right. Yep. No presentation. I'm just going to say a few words about ESCO and kind of our motivation behind doing this. So ESCO is the ESDIS Standards Coordination Office, and as the name suggests, we coordinate standards activities for NASA's Earth Science Data Systems. So I guess some of the most important parts of that is, one is that we maintain a list of approved standards for use in NASA's Earth Science Data Systems, and we manage the process by which new standards are approved. So we do stuff connected to standards, and we all like standards, don't we? And as the old saying goes, the nice thing about standards is there are so many of them to choose from, and that's part of our role, is really to look at the landscape that's out there and help ESDIS identify which standards we should be using in our data systems. So standards are good. They one, they save us work. We're building on the knowledge of people that have gone before. We don't have to invent our own data formats. Very importantly, they aid interoperability. If we're all using common standards, that helps us to work with other people, helps us to work using multiple data sets from different sources. And the other thing that standards help to do is to build a tool ecosystem. So if we're using common standards, that's a motivation for tool providers and other people in the community to build software and tools that support the standards that we're using. So, standards are a good thing, but we need to choose the right ones. The standards that get approved by ESDIS, before they become a formally adopted standard, they have to be prone to be kind of production ready. So usually that means we need operational evidence of use before something can be approved as a standard. I guess my other take on standards is it's a bit like waiting for a bus. You can sit around all day and all of a sudden 3 turn up at once. You don't know which one to get on. And that's kind of where we are now with some of the new and emerging technologies. So, looking forward to hearing from some of the people we've invited along this afternoon who've been working in these areas of new and emerging technologies and kind of experimenting with some of the newer standards that are around. So we're interested to hear, both about what they've done, what they found out, maybe what didn't work so well. If anybody wants to speculate on where things are going in the future, that would be good too. So I think from the ESDIS Standards Coordination Office perspective, this is part of our outward-looking part, looking at what are the emerging standards. So any hints that you can give us on things that we should be paying attention to are very welcome. So welcome everybody. Ed, back to you if you'd like to.
Yes, thanks for that, Steve. So now we're ready to move into the speaker and presentation part of this session. And I forgot to mention, but the order will be Li Ping, and then Amy, and then Alec, and then Doug. You'll be wrapping up. So go ahead, take it away, Li Ping. And again, let me see. I see you are in kind of presenter mode right now. Maybe something with your monitor or something you need to switch. I would say maybe if you can't put it in presenter mode, just leave it in non-presenter mode. Might be a better experience for the audience.
Just need to click swap displays at the top.
Yeah, swap displays, but where do you, oh, I see on the top left there. Do you see that, Li Ping? It says swap displays.
Swap display, which one? You cannot see it, or?
We do see something on the screen, but it's in the presenter mode where we see all the slides along the bottom. We see a main slide, but
yeah.
From the real, yeah.
Just
so on the top left, there's a swap displays option. I think maybe if you click that might solve the problem.
Yeah. Can you see it?
There you go.
That's it. Perfect.
Yeah. Okay.
So
okay.
Go ahead, Li Ping.
Okay. Thank you, everyone. And I'm going to talk about standardization with your spatial analysis ready data through ISO and OGC. I have a colleague, Li Yingguo, and also from OGC, Joshua Lieberman, as co-author. So I first, introduce why we're going through the ISO. ISO is an international standard organization. They have many different technical committees. And one of the technical committee called TC211 is responsible for setting international standard on geospatial information. It's also include all the remote sensing standard in the ISO. So this is ISO. ISO is TC211 is a membership. Country as a membership. Currently, they have 37 so-called P member participating member country and 33 observing member country, and then they also have 27 internal liaison organizations. This means they have other ISO TC that work related to the geographic information or remote sensing. So they have an internal liaison, and the external liaison is to the external organization like OGC, like IEEE, like GEO. They are all the external liaison, and then internally, work on the project. They have 6 working group. And the working group underneath the working group have a project. So individual standard project are sitting underneath the working group. And so this is ISO and ISO TC211. Each member country, they have a national committees that represent the country in the ISO TC211. In US, this national committee is the INSA L1, International Committee on Information Technology Standard, and L1 is the Technical Committee on Geographic Information. And like NASA, like USGS, FGDC, like ESRI, or the member for INSA L1. So this is the organization structure in ISO TC211. And the open geospatial, just skip this. Everyone knows OGC is a member. And the relationship between the ISO TC211 OGC and the CLS is, the CLS is external liaison organization for ISO TC211. OGC is also external liaison of the ISO TC211. The difference between external liaison organization and the P member is that if we come with a standard, voting approval standard, the only P member can vote, but the liaison organization cannot vote. but they have a right to, lead the project, standard project, and doing the standards. So this is a difference between the liaison organization and country member. So I have ISO. So the OGC actually have a very special status with ISO TC211 because the two organizations signed cooperative agreement. They want to converging the standard development efforts. So make sure that ISO and OGC standard are not contradictory to each other. So OGC and ISO TC211 establish a coordination group called JAC. So joint ISO TC211 OGC coordination group. This coordinate ISO and OGC activities. So we come back to the the standard activity I going to discuss is called analysis ready data. The concept of analysis ready data was initially developed by CIOs, and the motivation is that the currently you have so many satellite remote sensing data, and a lot of data need to be further processed in order for user to use. So the ideal situation is that the user can, the space agency can produce the data product that conform with certain specifications that the user can take the data and can immediately be analysis with a very minimum additional process requirement. And this is basically the definition of CIOS ARD. And the CIOS ARD activities are CIOS-wide initiative, and CIOS has developed a number for ARD specification. And one of the group in the CIOS called CIOS ARD Oversight Group manage CIOS-wide ARD specification development activities. And CIOS, have put out a number of ARD specification, and they, encourage its member agency to produce data in ARD conformed product in form. So this is the current situation in the CIOS. And so why we need to go through standardized ARD specifications through the ISO and OGC. First reason is that CIOS is not a recognized standardization organization. So the specification from CIOS are not considered as an international standard. Second reason is that CIOS ARD specification has not gone through a rigorous standardization process with a broader community consensus. Because basically this is a group of people from CIOS member agency. They work together and develop the specification without the input from like a commercial sector, from academia, and from user. So this is something that we need a broad involvement. And another thing, because that currently the CIOS ARD specification is mainly used by CIOS member agency, and we need to expand the adaptation by non-CIOS member, especially commercial space activities. So this is and another reason is since the CIOS ARD specification is not international or recognized standard, so they cannot be adopted as a national or agency standard, and cannot legally put into like a contract or requirement. Say a contract, if you provide the data, you have to comply with such a standard. But so this the basic motivation. We want to broad the adoption of the ARD concept and the specification by broad community and become authentic standards. So this is some history on the standardizations ARD through the ISO and the OGC. With CIOS support, OGC Disaster Pilot 2022 include the action item to develop a recommendation for ARD standardization. So this is some initial recommendation. We recommend use the CIOS ARD spec as the base and building on existing OGC and the ISO standard, and this to be a joint ISO and OGC standard developer efforts. So we're going to develop a standard that based on CIOS ARD specification, but this will publish both as ISO and the OGC standard. So the content will be exactly same. The cover will be ISO standard, and on top we'll have an OGC cover. So in MOU between ISO TC211 and the OGC allow OGC to do that, so they can adopt the ISO standard and put the OGC cover as an OGC standard. So this is we want to go through a formal standardization development process and publish both as OGC and ISO standard. And the plan will has been briefed to CIOS ARD oversight group, CIOS WIGS, CIOS CalVal, and also CIOS SIT, strategic implementation team, and also OGC and ISO TC211. And they all support such kind of plan. And we envision the ARD standard will be a multi-party part ISO and the OGC standard. And the part one, we're going to be a ARD framework and fundamentals. This will set as the overall framework for other ARD specification to be plugged into the overall framework. And then we will define all the common elements in this part one. And the other part is the ARD specification, for example, for land, for ocean, for atmosphere product, for product from Earth system model, and the geospatial ARD surface. But this just those parts just initial thoughts. Once we establish the project team and the standard working group, then it's totally subject to the project team and the community decide how we're going to organize the ARD into different parts, different specification. But those are just initial thoughts. And currently, we have prepared two documents. One is the OGC, OGC ARD standard working group charter, and another is a new work item proposal for ISO. You need, in order to start a new project, you need submit a new work item proposal and get the all member, P member country voter agree, and also at least 5 country participation in order to start the project. So we have prepared both document. So from the OGC side, the OGC, we are going to set up as the ARD standard working group. And this working group, we have for the ISO, as I just mentioned, OGC is the liaison organization of the ISO TC211. So OGC can submit the new work item proposal to ISO. So OGC already submit the new work item proposal to ISO TC211 through the joint advisory group. And as I mentioned, we have at least 5 P member countries needed to nominate experts to be to the project team in order to project to start. So we currently, we have a US, China, Canada, Japan, Australia, France, and Germany, India. They all express interest to be the project team for ISO. And meanwhile, in the OGC, we going to share the same. Most people will be overlap between the OGC ERD standard working group and also ISO project team. So basically, we have a two head and same group of people. So the ARD standard working group charter, as I mentioned, that we drafted the charter in May 2022, and the charter was extensively reviewed by CIO's ARD oversight group and the OGC member. And the draft charter presented at 124 OGC member meeting in October last year, and was released on the OGC website for public comments for 1 month public comments. The public comments period ended by December 21st. So we're going to have a final presentation to OGC member in on next OGC member meeting in Frascati in February. And once presented, then OGC can issue a ballot for member to vote. And I have no doubt that we will get the charter approved. And meanwhile, ad hoc ARD standard working group meeting is scheduled in same week in the Frascati. So this is a current ARD standard working group status. And this is the initial charter.
It's Ed here. You're at the 15-minute mark. I can give you a few minutes more, but please.
Yeah, just two more slides, okay? So, and this initial member of the charter member. And the ISO, as same thing, we have a new work item proposal submitted, and I expect the officially the project will start in May of this year. And so we, how to join ARD standard project. We want to broaden involvement of Earth observation and the geospatial committee in ARD standardization. And so anyone interested in participating in the OGC or ISO, of course, you can email me and I will tell you how to join. Basically, your organization needs to be OGC, either OGC or ISO member. And so welcome everyone, to join this standard activities. And that's all for my presentation. Thank you for your attention.
Okay, thank you, Li Ping. Fantastic. There's already some questions in the chat there, but the way this is going to work is we're going to start addressing those after we get through all the speakers.
Okay.
And yeah, so you can stop sharing, Li Ping, and we'll move on to the next speaker, Amy Barcia-Uskas from Seed Development, who's going to talk about the cloud optimized data format. So you have the screen already up, Amy. Go ahead and take it away.
Cool, thanks. Yeah, hey everyone, my name is Amy Barcia-Uskas. I work at a company called Development Seed. We work really closely with a lot of organizations, but in the context of my work, my projects are usually working with a group at NASA called the Impact Group. So I didn't add a little introduction slide here, but I work on a project called MAP. Actually, Doug Newman also works on that project, the multi-mission algorithm analysis platform, as well as a new platform called Beta. So as a sort of data engineer on those projects, I'm working a lot with cloud optimized data formats and basically trying to figure out exactly what what types of data formats and APIs we can build on top of these geospatial data archives in order to provide the scientists that work on those platforms with access to all the data that they need. And as I'm sure we all are aware here, given the growing volume of data, this is becoming absolutely necessary in order to scale science to the size and potential of those archives. So I'm presenting on behalf of a very large sort of community of geospatial engineers who have previously done development on these cloud optimized data formats and APIs. And I had to include this kept popping up into my head while I was developing this presentation, because it's kind of my disclaimer slide to say, hey, especially this being a standards conversation, this is an evolving ecosystem of geospatial standards. Like, a lot of these things are still sort of being worked out. And that's kind of why we're here today to talk about this, right? Because we're not sure exactly what is the format that everybody's going to be going towards. There are some formats that are becoming standard, but there are still a lot of formats, especially when you get to vector and point clouds, that are still sort of, people are still trying them out for the first time. They're still trying to understand these formats and why they may want to use them. So there's this really great study that came out, I think, a couple of years ago now, and actually some of the authors are here with us today. I think Dana and Patrick are here, that does this cross-format study of different cloud optimized data formats that have been coming out. And there's a lot of really good insights in this study. And I think, rightly, it sort of identifies the fact that there isn't going to be one format to rule them all. There's value in a lot of these different formats. And when you start to look at the different attributes or the different criteria that you might want to compare formats on, you can see that some formats like HDF in the cloud are really strong and support, sort of very heterogeneous support for a variety of data types and structures. Whereas other formats, such as, cloud optimized GeoTIFF, do really well when it comes more to things like standards body approval or programming language support, right? Cloud optimized GeoTIFFs are really widely supported. So you can see you're always trying to make these trade-offs. So what makes cloud optimized data so challenging? So there's no one-size-fits-all approach. While all Earth observation data is remotely sensed, this data may be processed into raster, vector, and point cloud data types and stored in a long list of data formats and structures. I believe there's over 160 raster drivers in GDAL or something crazy like that. A lot of this is user dependent, so it really depends on the users learning new tools and how to access that data, and they all have different use cases too. So how you're going to want to store that data and provide access to it is also depending on the use case, right? Like, are you looking at row-based access versus column-based access? But hopefully only a few new methods and concepts are necessary. So when we start looking at specific formats, that are coming up, one thing that's nice is that we do sort of start to see themes in these formats, and we could talk a little bit more about what those themes are, but I'll just, one more slide about the challenge aspect of it, which is, again, you're making this trade-off between sort of generalizability of some of these formats and specificity. So you can really pick out some formats that are going to be very specific to a particular use case and really come up with a spec that's really designed for a certain use case. But then, of course, you lose the generalizability aspect of it. So this is just another table from that Task 51 study, looking at how these different formats perform across different data types. How they're supported. And definitely there's a lot of other interesting insights in that paper as well, if you want to look at some of the performance tests that they did. So what is consistent across cloud optimized? What does cloud optimized mean? So to me, the way that I really simplify it is basically it's these file formats that are read oriented to support partial reads and parallel reads and random reads. And that means that basically you can support things like lazy loading and intelligent subsetting. So file metadata in one read. So when you're accessing data over the internet, latency is high when compared with local storage. So it may be preferable to fetch lots of data in fewer reads. This means that what we really want is an easy win with metadata in one read. And so that can be used to read these cloud native data sets where there's small addressable chunks via files, internal tiles, or both. So again, it's accessible over HTTP using these range requests. This makes it compatible with object storage. It's basically this, simple storage, simple storage service like we see with Amazon S3. And then we can parallelize reading it across many compute instances as well. So like I mentioned, this supports lazy access and intelligent subsetting and integrates with high-level analysis libraries and distributed frameworks. So again, you're not just storing your data in these formats is not going to do you any good without putting the right libraries in front of it in order to be able to read those formats. Okay, so as simplified as I could make this table, I tried to do so. So we have the formats, these cloud optimized formats on the left, and then the data type that they're usually used for. So cloud optimized geotiffs are being used a lot for raster data, and that's probably the most widely adopted cloud optimized data format that we see. For multi-dimensional raster, we're seeing a lot of adoption of ZAR and the Kerr-Chunk framework for creating ZAR metadata. From point clouds, what we're really seeing is we've seen a lot of end-to-end point tiles, which is good for this exploded version of point clouds. But we're also seeing now people gaining interest in cloud optimized point clouds, which is basically a cloud optimization on top of the traditional file format of LAS. And that's cool because it's sort of very analogous to the way that we're doing cloud optimized geotiffs. Everybody was previously familiar with working with geotiffs, and so just put some additional requirements on top of these formats that previously people are used to working with to make them accessible in a cloud optimized fashion or for partial and parallel reading. And then for vector formats, we're seeing a lot of interest in these flat GeoBuff and GeoParquet. So, this is sort of a standards conversation as well. We want to figure out what's being widely adopted and having some standards. So as I mentioned, COGS have been widely adopted, and there is some OGC standard available for comment. ZAR is also being widely adopted, but especially in specific communities. And I believe there's some OGC community standard in development for ZAR as well. And then when we get to point clouds and vector formats, these are sort of less common, less commonly adopted formats in terms of cloud optimizations, and no known ESDIS or OGC standard that I am aware of. I guess there is a draft OGC standard for perhaps GeoParquet. Okay, so what are COGS? So COGS are raster data representing a snapshot in time of gridded data, for example, DEMs. They're a de facto standard with an open OGC standard under review. The standard specifies conformance to how the geotiff is formatted with additional requirements of tiling and overviews. Again, COGS have these things called IFDs, internal file directories, which are used to tell clients where to find different overview levels and data within the file. Clients can use this metadata to read only the data they need to visualize or calculate. The internal organization is friendly for consumption by clients issuing HTTP GET range requests. And that's something that we'll see as a commonality across these different data formats, different formats targeted at a cloud optimized single file format. ZAR is the other format targeted at gridded data. So in this case, ZAR is used to represent multi-dimensional raster data or data cubes. It is chunked compressional n-dimensional arrays, and the metadata different from cloud optimized GeoTIFFs, the metadata is stored external to the data files themselves. So the data itself is often reorganized and compressed into many files, which can be accessed according to which chunks the user is interested in. So ZAR is not just a way to store data. It's not just a way to store data in ZAR specific design files. You can also create ZAR metadata for archival formats, and that enables you to get the benefits of partial and parallel reads for archives that are already stored in NetCDF4, HDF5, GRIB2, TIFF, and FITS. Also, since we're talking about standards, it's important to note that ZAR specs are in development. There are previous specifications for ZAR v2. Specifically, however, there's a cross-organization working group has just formed to establish GeoZAR standards, and includes representatives from many orgs in the industry. So this is placing additional geospatial specifications, geospatial conventions on top of the ZAR format. In addition, there's a proposal for ZAR v3, which will address challenges in language support and storage organization to address the issues of high latency reads and volume of reads for the many object stored. Okay, cool. So then moving into point clouds, there's this format COPIC, or there's many different ways to pronounce it, I guess, but it's essentially, so this first bullet just says, point clouds describes point clouds as a set of data points in space, such as gathered from LiDAR measurements. COPIC is a valid LAZ files similar to COGS, but for point clouds. So COPIC is just one file, but data is reorganized into a clustered octree instead of regularly gridded overviews like for COGS. So there's two key features: support for partial decompression via storage of data in series of chunks, and then also VLRs, or variable length records, can store application-specific metadata of any kind. So limitation is not all attribute types are compatible. Moving more into vector formats, we can start to look at flat GeoBuff, which is a very complex format. Again, this first bullet just describes vector data in general. So vector data in general is traditionally stored as rows representing points, lines, or polygons with an attribute table. Flat GeoBuff is a binary encoding for geographic data. So flat buffers are a generic data storage format that hold a collection of, so flat GeoBuff is basically built on top of flat buffer, is a specification on top of flat buffers for holding a collection of simple features. It's row-based, streamable, spatial index, optimized for remote reading. It has OGR compatibility, working with OGR APIs such as Python and R. And again, it works with HTTP range requests. Limitation, not compressed specifically to allow random reads. We've also found that it is another limitation is that there's no way to append. So there's no way to append data. So you really want to use flat GeoBuff, at least at this point, when you have the entire archive of this particular data store, not when it's a ongoing data set. For GeoParquet, so this is the first time we've talked about columnar data storage, but columnar data storage is also a type of storage that's gained a lot of popularity and importance in analytical use cases because of the way that it allows you to do analytical type queries on a large data archive. So something like give me all points with height greater than 10 meters. So this is GeoParquet has gained a lot of interest for very large archives of vector data, and it also is building on top of Apache Parquet, which is one of the more popular columnar storage formats out there. Cool, yeah, and then the rest of this is just sort of a little bit more details about GeoParquet, recent support added to GeoPandas as a distinct function, our support with GeoArrow, potential for cross-language in-memory shared access, specifications for spatial indexing, projection handling, et cetera, are still in discussion. Again, so there's many that I didn't get the chance to mention here. I just highlighted the ones that, seem to be the most popular across the different types of data at this point. And also just had to mention in here that, all these data formats are awesome and important, but what we really, it's not going to mean anything if you don't actually publish metadata about it. So I love this quote. I think it's from Matt Hansen. If your metadata is not indexed, your data does not exist because nobody can find it or know what it is. So that's my plug for Doug's talk on Stack. That's it. Oh, and then I just have a bunch of resources. So this is a link to a lot more information about all the formats that I talked about.
Thank you, Amy. Yeah, almost right on time, just 16 minutes. So thanks for keeping us on time and that fantastic presentation. There's already a few questions in the chat that we'll get to eventually. I wanted to remind the audience, if you want to go or follow along with the presentations, at least the first three are on the session homepage, landing page. So you can just go there, including the talk just that Amy gave. And sorry, Amy, for misspeaking your last name there earlier.
No worries.
Okay. Yeah, thank you. Okay, Alec, are you ready to go? Alec Jelinek from the HDF5 group, going to talk about HDF5 in the cloud. Go ahead and share your screen, Alec, and you have the floor. 15 minutes,
yeah,
please.
Sure. Yeah, keep me honest.
We do have extra time, but just want to keep the ball rolling, so to speak. We see your screen.
I hope people see it.
We see your screen. There it goes in presenter mode.
Excellent. Excellent. So I am from HDF group. HDF5 is the library and the file format, but that's okay. Yeah. So I'll be talking about cloud optimized HDF5 files. And since Amy talked about cloud optimized format and explained range gets and everything else, I'm kind of not going to spend time on that. The point being, I will say that, so what I'm talking about now is how to instruct HDF5 library to range the internal structures of one HDF5 file to make it more so that data access in the cloud object stores becomes more efficient. And so that's what I assume when I talk about cloud optimized. I also have definition of what I think is cloud native, and that, for example, would be ZAR, or what HDF5 cloud native schema also does. So for that, I'm going to skip these things, not to mention because Amy already mentioned range gets and all the other stuff. So why optimize cloud optimized HDF5 files? Well, first of all, I don't think that this is fairly known. And since HDF5 is as a format is much more capable than say GeoDiff, I think it would be very nice if HDF5 files would be able to be cloud optimized. And also, hopefully, with cloud optimized HDF5 files, there's the least amount of reformatting from the archives to the cloud object stores. Very relevant to things like Kerchunk that Amy said is the fast content scanning when these cloud optimized HDF5 files are in an object store, and efficient data access by cloud native applications. So in other words, the predecessor of Kerchunk was actually a result of my work with USGS. And as a result of that work, we actually compared performance of completely equivalent ZAR dataset and one HDF5 file, the same compression, the same chunk sizes, everything, and there was no difference in performance. And so that's, I think those kind of things can really help people to actually enable access to HDF5 data without too many reformatting and data duplication. Let me just remove this. How do we remove this from me? I can't see my top of the screen. Doesn't matter. I remember my slides. So properties of cloud optimized HDF5 files. One is this paged aggregation. It's one of the available file space management strategies. And when it's set, it instructs the HDF5 library to write out bytes in a certain way. And that's important, the way how it writes out things. Another property is large data set chunk size. This is really critical, and strictly speaking, you could do this in current HDF5 files even without page aggregation. And so that's a possibility even now. Chunk compression, obviously, if you're working with large chunks, then how much time it takes to decompress and what kind of compression algorithm is used can play a role. And also, last one, minimal use of variable length data type. And that's really relevant for those who are accessing these files outside, not using HDF5 library. And I'll visit this thing briefly. So variable length data types. They're not really good for cloud optimized HDF5 files, mostly because the current way how they are stored in HDF5 files is not really friendly to range get requests. And so if you happen to have a lot of variable length data types, first, I would recommend don't use them. And two, keep them at the minimum or use something that has sort of a fixed length to it. And that enables HDF5 library to group these things into a block that can be range get. Luckily for the ESDIS data, that's not the case. So that's really for others. And when I say variable length data types, also because a lot of libraries use HDF5 library to write out data, you really have to look closely inside the HDF5 file to the low level storage settings to really see whether or not your data is variable length. So even if you are using some other library that doesn't explicitly tell you that you're going to have variable length data type in HDF5, that may actually happen. So that's something to think about. Mostly how currently, for example, Kerchunk or DMR++ in Hyrix do it, they basically just copy this data into their own sidecar files and deal with it. Large data set chunk sizes, when I say chunk size, I mean size in bytes. So chunk shape is essentially the number of elements along each dimension. And those two things are connected, obviously, but I'm here talking chunk sizes in bytes because that's what we're talking about here, making transfer of data from cloud object store to an application. And so there's this AWS best practice document from a couple of years ago, maybe several years ago now, that says about 8 to 16 megabytes is optimal for every range get request. Maybe, maybe not, but I'm just mentioning it here for completeness. But once you agree to essentially a decent size for one range get request, then obviously you can work backwards how much, for example, you want to have in your chunk, how much your chunk shape should be, and then work backwards how many chunks you want to include in your request and all the other things. But obviously, it is possible to create large dataset chunks in HDF5. A lot of best practices and a lot of documents on the internet are basically for smaller chunks. One reason that I want to mention here maybe is because there's this thing called dataset chunk cache in the library, and the library comes up with a default size on 1 megabyte, which is kind of for these days, and especially for cloud optimized access, kind of small. And so you can configure it, you can set it up to whatever size you want per dataset. And so, so think about it, both when you're writing out data and when you're reading out data. That can really improve performance a lot. Oh, I forgot to mention. So when I say dataset, I'm talking about HDF5 dataset, which is the equivalent to netcdf variable, which is equivalent to ZAR array. Just so that people don't think when I say dataset, then I'm in a file. All right. So what is page aggregation? It's one of the file space management strategies that the HDF5 library uses when it's writing out bytes that belong to one file. And it is not default. So, and unfortunately can only be set when the file is created. So it's kind of too late now for all the existing HDF5 files, but there is a way to change that. And also, because this instructs HDF5 library to write out bytes in a specific way, this specific file space management strategy is really applicable to new files when the content is basically written out once and never modified, which I think fits very well into a lot of workflows, that the files are created, sent to their merry home, and be used until they get overwritten with something new. So modifying files rarely ever happen. So what is the basis and why page aggregation really is important for cloud optimized HDF5 files? Is because HDF5 library writes out bytes essentially in pages, and it divides these file pages either to belong to internal file metadata or to actual data. And if, when instructed to use paged aggregation, and if this page new file page size is properly sized, then it may happen that all internal file metadata essentially happens to be written out in one contiguous block in HDF5 file. And so therefore makes it super easy to retrieve the entire file content and where is what in one single request to an S3. And again, as I said, so you can have everything in one page, or you can have more pages, but you know, one more way you can have it in one. How to apply page aggregation? So this is in this part. So for existing files, you have to use the H5 repack command line tool that comes with the HDF5 library, and this is the command line basically. It says I want page aggregation. This is how many bytes is going to be in one page. Input HDF5 file, output HDF5 file. For those who are creating files and have, you know, using software and code, obviously there's many more, but the two critical things are these two lines here that set file space strategy and what the page size is going to be. So page buffering. This is a low-level cache in the HDF5 library available only to files that are created with paged aggregation. And this is a low level in terms that at that point, the HDF5 library still doesn't know are these bytes part of specific HDF5 dataset or not. All that the library knows is that there is a internal file metadata pages and there are data pages. But what it allows you to basically keep these pages in memory so you don't have to repeat your request into the object store. And here's a case study. I used an ISA2 file, ATL03. This file is 2.3 gigabytes, has 171 HDF5 groups and 1001 HDF5 data sets. And this next line, this metadata file size is really the critical number. So it's 7.7 megabytes. That means that the internal description of whatever is in the file and where it is in the file is in this 7.7 megabytes of the entire file. And what I've done is now I used H5 repack and produced the same version of the file using 4 megabytes and 8 megabytes file page size. And I use page aggregation. And then I put all those 3 files into an S3 and I tried to do some performance study. And so here is the command line tool. There's another command line tool, H5 stat, that it can tell you, given the HDF5 file, what is the file metadata. You can see it here. So that's the number. And you can see the default file page size is up here, and it's only 4 kilobytes. So when you see now all of these HDF5 files that you now have are having all their internal file metadata scattered throughout the file in 4 kilobyte pages, which is the real reason why right now all these files, if they're just dropped into an HDF5, in the store of some kind of object store, would really have issues and yield very bad performance. Anyway, so case study, 3 files in Amazon S3. I wanted to list file content and I wanted to find where the dataset chunk file locations are. And this is a very common task. Anyone like Kerchunk or like DMR++ for a Hierarch server or even a high HDF scalable data service, they all depend for this kind of information for later workflows. And so I tested it using H5.537 and HDF5 library 113.1, but in the meantime, H5.Py has a new release, 3.8, and HDF5 library actually has a new version 1.14.0, and everything works. Basically, I highly recommend these latest versions, obviously. And so I have computing environment, I have my EC2 instance, everything is in the same AWS region. I'm using Python 3.11. And I'm basically accessing these files with the HDF5 library in an EBS volume that counts as a local file system. Then I'm using HDF5 library's own read-only S3 virtual file driver. And then I'm also using HDF5 library with S3FS Python package, because HDF5 library through H5Py can actually use any Python file object. And here are some results. So first, how much time it takes to repack this ISA2 file. And these are the times with different file page sizes. How am I doing it? I'm coming close. I'm good? All right. Okay. So I use
you're good. Like for another few more minutes, please.
All right. So 4, 8, 16, 32, 64. You can see the repack time fairly similar, and file size changes. Because now when you use this page aggregation and you set up the file page size, any unused space on a page, gets basically like a free unused space. So the new files are going to increase in size. And I use bigger page sizes only in case people want to have more chunks in a single page. But you don't have to go there. And so here are the performance results. So I use the local file system HDF5 library. Here is the original file, and there are the versions with different file pages. And also I'm using different sizes of the page buffer that I mentioned. And I divide their time with some kind of performance ratio. And so if performance is 1 or less, that's good or better. Anything above 1 is kind of, not good. But as you can see here, it's kind of very close to each other. So that's okay. The fun part begins when we move to these files in S3. And with the library's own S3 virtual file driver, you can see how much time it takes, how much more time it would take to collect all this information about the HDF5 file. However, as soon as you switch to a cloud optimized HDF5 file, the time becomes basically comparable to this file in a file system. And I also use S3FS. However, in S3FS case, there are a lot more knobs that you can turn and configurations that you can set. So it's a little more complicated to find all the options. But anyway, again, once you start using cloud optimized files with enough page buffer, things really start to look exactly almost comparable, unless, if not a little bit better than when the file is in a local file system. And so wrapping up, I don't want to take much time, but again, there is a way to create cloud optimized HDF5 files, and they can perform, especially for this common test, as same as the file, that file in a local file system. Page buffer obviously helps. There is a setting in HDF5 library supported by the H5Py that you can look into the statistics and try to optimize things if you want, so that you can really find the right settings for that. And if you're actually using S3FS, think about that. Actually, it comes with the default range get request block, which is 5 MB. And so sometimes it's too much for you to use, sometimes it's not. So think about that when you are trying to improve your X. And that's it. I would stop here. Thank you.
Thank you, Alec. Thank you. There we go. Great presentation. Great work.
Thank you.
All right. Without further ado, I think we'll move on to our final speaker. That would be Doug Newman, and he's going to be leading a discussion and an overview of Stack. So, Doug, can you unmute yourself and take it away?
So I hopefully am unmuted, and you should be seeing ESIP's wonderful homepage. True story?
Yes.
Excellent. All right. So I'm going to talk about Stacks as a standard for cloud-based data discovery. My name's Doug Newman. I'm a system engineer for NASA ESDIS at Goddard Space Flight Center. Stack means spatiotemporal asset catalog. So if you have a catalog that conforms to the stack specification, you have a spatial temporal asset catalog. So I'm not confident this is going to catch on, but onward. So what is stack? Stack is a common structure for describing assets and cataloging them in spatial temporal terms, those assets being imagery or data in the form of SAR, point clouds, data cubes, etc. There's a stack specification which defines how to describe assets so they can be more easily leveraged, indexed, and discovered. And then there's also a stack API specification, which defines how to find those assets, describing a queryable dynamic version of the spatial temporal asset catalog. So why is it being proposed as an ESDIS standard? Well, sometimes we find a standard and sometimes the standard finds us. And in this case, Stack found us. We had a previous attempt at selecting an interoperable search and discovery standard for the earth science domain, which was OpenSearch. And that generally worked, but suffered from a lack of wide adoption, even though it was quite successful in the area of WGIS Quick and federating agencies' catalogs together. It didn't really have much of an uptake outside of that. Stack aims to fulfill the same remit that we propose for OpenSearch, but it probably better fulfills the selection criteria for a standard within ESCO than OpenSearch did. Number one on that list of criteria is a large, vibrant community supporting it. Evidence leads ESDIS to believe that this is how the earth science community wants to discover and consume assets in the cloud. And consequently, ESDIS regards Stack as an essential component of EOSDIS's cloud evolution strategy. With respect to Stack, this is happening at a rapid pace, facilitated by the provision of tools and services that are Stack compliant. For example, Stack Browser or Intake Stack and Stack Server. We're currently looking, hopefully, at the Stack Index, which keeps track of how Stack is being used. We currently have in here 40 Stack APIs, 92 Stack catalogs, and 47 different software and tool offerings. So another criteria that we'll look for is a solid technological foundation. Stack is built on HTTP and JSON, gives a simple API that portrays results in a format that community can easily consume. This is Postman here, hopefully you can see it. We're doing a simple GET request on CMR's Stack API for the collections associated with PODAC. What we get back is basic JSON describing each one of those collections. And I'll come back to this in a moment. So we're also looking for a lean core specification that can be extended without compromising interoperability. And Stack Core concentrates on just the spatial and temporal properties of the data and its assets associated with them, nothing more. And this enables interoperability by facilitating a very small footprint that everybody can get on board with and not become niche too quickly so that certain adopters shy away from it. And that satisfies many use cases. In Stack's case, extensions can fill in the gaps while remaining backwards compatible with the core. And we can therefore maintain interoperability without sacrificing functionality. So we support a large number of use cases. Let's switch back to the Stack browser now. While this standard has evolved into the de facto means of the discovery and portrayal of geospatial data in the cloud, there's nothing cloud specific about the catalog or API specifications. So the standard could be used for any online geospatial catalog service. The catalog specification itself allows the data provider to arrange the hierarchy of their catalogs in any way they see fit. This opens up the possibility of portraying your data in a number of intuitive structures, You could have temporal drill down by year, month, and day, spatial drill down by path row or by country, state, and county, or drilling down through platform to instrument to collection, etc. And coupled with SAC's self-describing navigation support, we can cater for a large number of data discovery use cases. What I'm looking at here is a stack browser representation of PoleCloud's collection here, Sea Gliders. And you can see that it has a catalog inside it and also the items associated with its catalog. This is a very simple example. So not only do we have that provider collection granule kind of idea that we've very traditionally used in the past, we can also drill down temporally in the same stack browser instance. So I just drilled down on the year 2019, and it's telling me I can drill down further to the month of October, and then we've got the 3rd and 4th of October, etc., etc. But we're able to accommodate both of those things in the same subcatalog at this level, which is very appealing. And finally, and this is a bit more specific towards the search and discovery interoperability case, there's a lot of potential for federation here. The adoption of Helios and linked data by stack, coupled with the concept of hierarchical catalogs, lends itself to federated discovery in much the same way that OpenSearch did. Many federated catalog systems may want to adopt stack as a means of linking loosely coupled archives using two-step or even multi-step discovery processes. This is something that CMR are currently looking at in concert with CEOS for the Quick system, as we see more and more of our agency partners migrating to stack in favor of OpenSearch. It seems prudent to start providing that capability using stack as an underpinning as well. I'm looking again at this PODAC collection, CMR's stack catalogs. We could envisage one of the quick providers, say for example, INPI in Brazil or ISRO in India, in this manner as a catalog in CMR, where unlike PODAC, where the collection metadata is stored in CMR, but the file or granule metadata is not. So we need some means of taking the consumer of this from CMR over to equivalent file level stack API at, say, for example, ISRO. So we would have an ISRO collection catalog here with a set of collections associated with ISRO. And if we look at this element here, this is basically stack describing where you can find the items associated with this collection, the files or any other assets that you could portray. And although in this particular case, this is pointing to a stack catalog within CMR, this could point to a stack catalog at the item level in ISRO. And because of the self-describing nature of the stack catalog specification, this would be opaque to the consumer. They don't need to know that they're suddenly switching from CMR at NASA to a API at ISRO. The specification just guides them in that direction naturally. So finally, because I'm being really quick, ESCO has a stack RFC out for community, out to the community for evaluation. If you're interested in reviewing it, please get in touch with Steve, not me. And one last note, it's a stack, not a stack catalog. Thank you very much.
All right, thank you, Doug, for that nice overview. Excellent. And as you mentioned, yes, we are looking for some more reviewers for what we call the stack RFC that's under review now in the so-called the ESCO ecosystem. So we do, you know, all the standards that we eventually publish and promote, they all go through a pretty rigorous, very rigorous community review, not just inside NASA, but outside as well. All right, I think we're going to move on. Yeah, thanks for keeping us on time, Doug. We're going to move on to the Q&A part and discussion part of this session. So let me see, I maybe need some input from Steve about how best to proceed forward, or for the other ESCO stakeholders. I mean, there are some questions in the chat here that maybe some kick off the discussions. And I think we definitely want to get a questions to each one of the speakers at a minimum. What do you think, Steve? Shall we just maybe start off with the first set of questions that came in?
I think let's take a look at those, and I certainly think we've got some questions for all the speakers. While we're doing that, I'm just going to put a link in the chat. Oh, I thought I was going to put a link in the chat. Hang on. So in Slido, we do have a poll there, which is just like a word cloud. So we've been, our presenters have been talking about some of the sort of new and emerging standards that they've been dealing with. We'd also be interested in getting any further input. So take a look at that link I've just put in the chat, and while we're doing with the Q&A, feel free to add your own standards that you think ESCO should be paying attention to there.
Dave, this is Michelle. There's also some questions in the document, and I can pop those in chat or help to read those off, or just they're near the bottom of the document.
Oh, okay. So yeah, Michelle, do you want to just...
I was going to suggest maybe, you know, we kind of proceed forward with, you know, getting to some questions for each one of the speakers. Of course, we will have some kind of cross discussions, but yeah, Michelle, I don't see, can't kind of really monitor both documents, but maybe you can like jump in when it might be appropriate to, you know, relay a certain question to the audience or to the speaker.
Yep.
Okay, so let's, I'll need that to Ed Michelle for you to handle that. I see Alex has got his hand up. I don't know if he had a question before he went on.
Go ahead, Alex.
Yes, I did. So I'll ask. So there's a lot of mention of Kerchunk in chat and in some of the slides and whatnot. So my question is now with Stack. Stack is JSON, Kerchunk is JSON. Is there? I'm kind of seeing a lot of now different dialects of describing things in JSON, but eventually all point to the data somewhere. So in other words, my question is, what people think is Stack JSON eventually be good enough to actually point to data in the same way that Kerchunk JSON points to data, and so that we can all merrily agree on one single JSON dialect, all the way from catalog to actually data access, rather than to have these different dialects.
So at its core, no, because it's a very lean and lightweight. Basically, it's describing the spatial extent, temporal extent, and the assets associated with it. But I suppose you could get there by extensions, but that would be very difficult to coordinate, I think. That's my 2 cents.
Yeah, I mean, I agree, because the reason why I ask that is often I see Stack in the context of cloud optimized geotiff. And the way how everything is organized, it kind of looks to me like a single geotiff is one chunk of
yeah,
data.
I kind of think of Stack for cloud optimized geotiffs the same way that you think of the ZAR metadata, the JSON ZAR metadata for the ZAR store, right? It's creating the sort of spatial index of your cloud optimized geotiffs, and the cloud optimized geotiff itself is like a unit of data, where it's, you know, to get at the same aspects. So it's not standard across those two, right? But Stack is playing the role that ZAR metadata is playing for ZAR and NetCDF.
Yeah. All right, thanks.
So good, thanks for that, Alec. Maybe we'll circle back to the ARD topic. And Li-Ping, there's a couple questions that kind of popped up in the chat for you from Rama with regards to, you know, is the VCS ARD spec actually ready for standardization? And, you know, on the logistics side, is the OGC and is an ISO going to be proceeding on parallel tracks, or how is it kind of like that coordination going to happen? I think you touched about that a little bit in your talk, but maybe you want to just elaborate on that a little bit more.
Yeah. First of all, in terms of whether or not ARD is mature enough to go to a standard, we realize this problem because we think the ARD is going to be a change during the years. And so we select, so I also actually have a quick check and standardize. They have a called technical specification. This allow you to develop into international technical specification in very quick time, like around 2 years. And then once it becomes technical specification, allow you to revisit within 3 years and decide whether or not you want to revise or stay as is, or convert to the international standard. So we choose the technical specification route for develop the standard. We consider this going to be, we realize, this is not totally mature. In terms of logistics, we're going to have, as I said, we're going to have a basically a single team. We have two heads. One is OGC standard working group, another ISO standard project. So basically, we're going to have one single document. The document will be developed and exactly same in the form as OGC standard and ISO standard. So.
Okay, thanks for that. And I had a question too. Kind of germane to the point cloud format. So we're talked about a little bit later. I mean, I guess would it be fair to say what the ARD spec that CIOS has come up with and is kind of being proposed? I mean, that's really only for like raster satellite products at this point. Like, it can't really handle like point cloud formats, or could it be applied to point cloud formats? Is that a thing, or is that on the possible roadmap?
Currently the CIOS ARD specification is mainly for the satellite remote sensing imagery. So they are on the last data. But this was why we want to expand. We call geospatial ARD. So we want to expand the analysis-ready data into the vector world, like the polygon, point cloud, and as well as the vector that load network as this kind of thing. But this totally depends on the resource availability, or people willing to, because the standard development in the ISO and OGC depend on volunteer contribution from individual agency or country. So if NASA or ESAP or OGC, someone have a resource, they feel this need to be standardized, then they can initiate a new project in the ARD area. So, but we in the framework part, the part one, we will allow you to have the ARD specification for vector, polygon kind of geospatial data. Okay,
thanks for that. Now, the next question I think is addressed to you, Amy, in your talk about the cloud optimized formats. This is one from Tyler Christensen, who is asking about kind of the trade-off between going the Kerchunk route versus native ZAR. So are there kind of any additional benefits for just staying kind of like a native ZAR, or when is it more, say, appropriate to say Kerchunk your individual NetCDF granules and go that route for cloud optimization?
Yeah, essentially, my understanding is you're constrained to the chunk structure of your original files. So your NetCDF or HDF5 can be chunked themselves, or could be a smaller file format, and you're not going to. If you basically are storing, if you're storing your NetCDF at one day, right? Like your time step is like 1 day, and you're not chunking that individually, then you would actually need to, you're not chunking those files themselves spatially. You wouldn't be able to create a chunk based off of the spatial index, right? You would have to re-chunk that data essentially. So in that case, it might make sense to build a entirely new like ZAR data store.
Mhm.
I think
Yeah, so-
just to point out, I'm sorry.
No, go ahead. Jump in.
Oh, okay. So just maybe clarify. So what usually happens is that people convert netcdf or HDF5 files to ZAR. They actually rechunk and create bigger chunks in the ZAR than they are in their original file. And that's really what makes ZAR really work good. And so if you do happen to have HDF5 and HDF4 file with the same chunk sizes like ZAR, and you use kerchunk to access, there is no statistically is the same thing.
Okay, yeah, thanks for that, Alex. So, I mean, the next question here that I was looking at here kind of maybe goes to the larger audio or speaker audience here. Really, I think maybe both everybody can perhaps weigh in on this. And there was some kind of like technical chatter too with this question. So, you know, perhaps even Davis has another perspective, but it was about, you know, these cloud native changes to the HDF5. Are they usable in netcdf4? You know, that page aggregation you talked about, Alec, and the other kind of features that you talked about in your talk too, Amy. I know it's a pretty broad or a deep dive question, but maybe you can give some like opinions on you know, to this question from Peter McCary. And maybe I'll pass the ball first to you, Alex, since you specifically talked about the page aggregation with HDF5 data model.
Yeah,
using netcdf4.
Yeah, so I have not checked myself, but netcdfc library is using HDF5 library. So I would assume that should be possible. I'm not sure about whether or not on the netcdf library there is a way that you can set this thing up, but again, it should be doable. I don't see any problem not to do it.
Okay, Ethan Davis, do you have any comment on that? I know you had some responses there in the chat. I didn't read them completely, but maybe you can unmute yourself and jump in.
Yeah, hi. I think there to write the data in the cloud optimized format, the netcdfc library would have to do some work. I think to read it should just work. However, there's still issues in the C library and the Java library for netcdf around actually making good use of the being able to have lots of parallel stuff. So there's some issues around that, but the library should be able to read them out of the gate, I think. But as Alexander said, for writing, it definitely would need some work to make sure it's setting the right settings and all that stuff.
Yeah, is that on your guys' radar screen at Unidata to
the cloud optimized? We have been talking about it. We've just started in the last, well, maybe a little before we saw Alexander's poster at AGU. Maybe a little bit before that, we knew some about it, but we've talked about it. Yeah.
Okay.
So on the radar, but not immediate in terms of writing.
Yeah, fantastic. Thanks for that. Anything else I want to talk about with regards to HDF5 usable by netcdf in the cloud, or any other feature sets that the community should be aware of?
There was a question in the Google Sheet. What open source tools are being developed to use HDF5 data?
Oh, that's a good one. Alex, you want to handle that?
A lot. I mean, I don't know what specifically, but I think every month there is, I don't know how something between 10 and 50 papers published that use HDF5 globally. So and they all use, you know, as far as I know, open source mostly. But yeah, I don't know specifically what open source tools are being developed, but yes, I mean, a lot.
And I'll just say, yes, I agree, lots. SDF and HDF have a huge community of users and a huge ecosystem of tools that support that. So there's definitely lots of work being done in that area. Once the libraries are, using cloud optimized, there'll be a lot of, and using some other cloud things, being designed for the cloud. It'll be, good.
Thanks, Ethan. Yeah, I wanted to quickly circle back to Amy because there was one question I had too. I got from your talk when you had the two families of the point clouds and also the vector formats and stuff. And the line between them is kind of blurry. Could you talk a little bit more about when it would be appropriate to use say a point cloud versus a vector format for representing Earth science data? And what about ESRI shapefiles in the cloud? Is what's going on there? Because shapefiles have kind of traditionally been the it's a proprietary format from ESRI, but have been like the vector format of choice for the GIS community.
Yeah, to be honest, I haven't actually used shapefiles much myself, but I know I did post this link to a cloud optimized shapefile as an option. It was proposed by Paul Ramsey, I think, in a blog post. So I'm not sure that much action has been taken there. Vector formats can do point clouds, but the spatial index for Z varies. So the line between needing a point cloud specific format versus a vector format is blurry, and that's a note from my colleague Alex Mandel. But
so if you have like a vertical dimension, then the point cloud format is a format of choice, right?
That's my understanding. Yeah. And the other note that we were talking about was it depends on what type of querying you're going to want to do in terms of the actual format that you specify, because if you're going to be wanting to filter on a specific attribute, then you might be more interested in a columnar data store where you can do a filter based off a specific attribute versus like row based, which would be able to potentially pull full records faster than the columnar option.
Okay, thanks. Well, we're almost at the end of our session here. A few more minutes to go. I'm just kind of looking in the chat here. I think we covered most of the questions. There are maybe a few that I haven't gotten to, so I wanted to maybe just propose if somebody has a burning question, go ahead, raise your hand, or just unmute yourself and ask the question.
Yeah,
Anybody?
I just had a quick question for Leaping. You can probably answer it in a minute. What kind of content would you have in the ARD framework or part 1 document? Would there be general principles that apply to all?
Yes, we will talk as CRC-ARD has a framework and a governance document, and we will use this as a base and expand that into the part 1 framework, and we're going to have an overall ARD framework. We will divide the ARD into different parts, and this project team will decide how we're going to divide into individual parts, and this will be documented in the part 1, as well as common metadata, minimum calibration validation requirement. All those will be in the part 1. So the part 1, as I mentioned, that as a framework, we will set all the common part will be in the part 1. So this is the current thoughts, and we welcome experts to provide input in terms how to divide the ARD into different parts. Currently, in the CIOS, they have many different a lot of them defined at like a product level. And do we need to define the ARD in ISO and OGC standard at a product level or the product type level, or we want to do a little bit high level in terms like the like land for the all land product or what we can require such kind of thing. So currently just have some concept and the basic idea, and we want to set up the project team and the working group and start gathering experts as inputs. So, but as I said, fundamentally, we will use sales ARD as a base, but like the standard, we already have like ISO, have a metadata standard, have a format standard. All those will be used in the ARD standard. Okay, this will answer your question, Rama.
Yeah, thank you.
Yeah, nice to see you. I haven't seen you for many years.
Yes. Yeah, good to see you too.
Good. Thanks for that, Liping and Rama. Maybe one more question if there is one. And I just put in the chat, I'd like to get a response from just one last poll on based on what you've heard so far. What are the kind of like top burning topics that you think the ESCO should focus on? So appreciate your filling out that poll right there. But yeah, are there any maybe final questions or thoughts or points of topic? Okay, I think hearing silence, I think we'll thank the speakers and thank the audience for your participation. This was a really fruitful session, at least for me, kind of learning about new things and what different parts of the data science ecosystem people are working on. Maybe I'll turn it over to Steve. Thank the presenters one more time and turn it over to Steve for maybe one final closing word. And I think, Steve, do you want to maybe say a few words before we sign off?
I'll just reiterate what you said. I mean, I think we had some great presentations, so thank you to all of our presenters for joining us today. I think what I've seen here, I mean, some good information for us to follow up on, but also, showing exactly why standards are a bit complicated. There's a lot of new work going on here, and things are still evolving. So I know, Amy, you were mentioning, things like sort of, ZAR, which version where people are now working on, and that's what we see in an emerging technology area, that the standards initially are evolving. So if you're an organization like NASA or anybody who has a large archive of data, we don't want to be updating the standard every few minutes because the standard is changing. So we're looking for some sense of maturity before we settle on a particular standard. So thanks to everybody. I mean, interesting talks and a lot for us to think about. So thanks again for participating today.
All right, folks.
Thank you.
Goodbye.
Thanks to everybody else for joining us. Thank you.
Thank you.
Cheers, guys.
Thank
See
you.
ya.
Bye.